Right, welcome everybody to the 2025 March meeting of the Mornington Peninsula Astronomical Society. And a few things up here that have been in the news in the last month. We start at the top left. Saturn now has 274 moons, according to the IAU, the International Astronomical Union, which means it's got more moons than every other planet in the solar system combined, added up. Jupiter now only has 95 and is unlikely to get more. And that was picked up by the Canada-France-Hawaii telescope using the latest technology. The size of these moons were of the order of about 3 kilometres across. And then, of course, the question comes, what size does it have to be to be a moon, as opposed to a lump of rock floating around the planet? And as yet, there's no definition of it, but I suspect it's like the definition of a planet. Eventually, enough is going to be discovered that it forces the IAU's hand to have some convention, the same as happened with Pluto, and they had a definition of the planet, of what a planet is there because of all the exoplanets. So the same's happening with the moons. Currently, about a 3 kilometre diameter moon at Saturn is the limit of the resolution of the techniques that were being used. So, of course, as the technology marches on, they're going to get better and better resolution, and they'll probably find smaller and smaller lumps of them. Almost all of them are irregular moons. So that means that they weren't formed at the time of the planets, and so tend not to be in nice orbits like the ones that were formed at the time of the planets, the regular moons. Moving on across to the next one from it, we have the arrival today of the 2 astronauts. They're up on the International Space Station unexpectedly for 9 months. I'm sure they weren't complaining. They splashed down in the Gulf of Mexico, and of course online NASA had to say Gulf of America with that one. And they came down to a pod of dolphins as well. Sort of throw in a flipper sound there just to make it very clear. It's not sure whether they just happened to come down in an area where there were dolphins, or there was another boat behind the camera throwing them out to the side of the vessel at the time as a bit of a distraction. There we go. It's quite a size, the Dragon capsule. As if you watched the footage online of the frogmen walking their way around trying to attach the harnesses to it, you'd have to think surely there must be a better way of doing it, but it worked. They got there and they got back. As opposed to the one on the right-hand side, top right, which was the SpaceX one from a couple of weeks ago on the 6th of March. That was where it broke up in orbit its payload. They successfully brought it back and they caught the booster, but the payload unfortunately didn't quite make it and broke up and fairly spectacularly over the Bahamas there. Also during the month we had Firefly Aerospace, a private US company, landed Blue Ghost on the moon, which was due to survive a couple of weeks until darkness fell on the moon. It wasn't designed to go any longer than that. It landed in Mare Crisium, and I'll show you where that is. If you don't know where Mare Crisium is on the moon, you can easily see it with your eye in the sky. I'll show you that on the next slide. And they left 10 experiments on the moon behind. It's all as part of the Artemis mission. So aside from putting another retro reflector mirror up there for bouncing lasers off the site, they also sampled things like the lunar regolith, the soil, and they dug down a bit to look for any moisture in the soil as well as several other experiments. So they were pretty much calling that a great success, given that now they weren't the first private company to try and land on the moon. It's just that theirs happened to be a successful landing, whereas the other one, if you remember that they landed, I think it was named like Intuitive Machines or some name like that, their craft actually fell over on its side when it landed, and that was the end of its mission. It wasn't able to point successfully to the Earth for communication. Now, while they were up there, you see in the bottom left-hand side the shadow of the blue ghost on the moon there with the Earth in the sky. The size of this craft is the size of a small car, so we're not talking about a toy size. This was a decent size lander that actually went up and went there. They happen to also coincide. I'm not sure whether this was all designed as part of it or whether it was just pure coincidence, but several days after they landed there was the March 13. For us here on the Earth, it was a lunar eclipse. And if you're unfamiliar with how lunar eclipses occur, that's the middle diagram on the left showing the sun on the left, the Earth in the middle, and the moon on the right-hand side. And during a total lunar eclipse, you actually get Earth's shadow cast into space, and the moon passes through the shadow, and the moon turns a reddish colour in the sky, and that's when the media call it silly names like wolf moon, blood moon, and whatever else they can sensationalise. But it turns a reddish colour, and of course if you're on the moon it's going to be red, and that's what you're seeing in the bottom centre picture. That's the view from Blue Ghost, and as you see everything is looking quite a nice ghostly red colour, and effectively what you're seeing is the colours of sunrises and sunsets on the Earth have leaked around and are bouncing off the moon. So you see indeed it is a reddish colour there. On the right-hand side is the view from the moon. So our view from the Earth is that the moon turns a reddish colour, but the view if you were standing on the moon where Firefly was is you get the equivalent of a solar eclipse. So you see the reverse. So you see the diamond ring effect in the bottom right-hand one. Here on the Earth, if that was occurring, it would be the moon covering up the sun. In this particular case, it's the Earth covering up the sun. So in that diamond ring there, the dark black in the middle is actually the Earth, and you can see the light leaking around the edges. So you get a ring of light around it in this particular case. So it's a bit like an annular eclipse, one that didn't quite completely cover the surface of the sun. Okay, now Blue Ghost, as I said, lasted for several days, and then its power ran out. And this is what it then transmitted back to Earth. So it said mission mode change detected, now in monument mode. Good night, friends. So it was in mission mode while it was working, and then it was shutting down, knowing that it's a one-way shutdown. I will hold vigil on this spot in Mare Crisium to watch humanity's continued journey to the stars. And Mare Crisium is where the X is shown there in the centre there. It's that very familiar dark Mare on the moon that we see usually around the 8 o'clock position on the moon as we see it from the southern sky. Then they said, here I will outlast your mightiest rivers, your tallest mountains, and perhaps even your species as we know it. Which sounded rather ominous, given that they launched this before all sorts of things that are happening in the US. But it is remarkable that the species might be outlasted by its own ingenuity. So hopefully it's not too prescient. Here lies Blue Ghost, a testament to the team who, with the loving support of their families and friends, built and operated this machine and its payloads. And that was sent Monday morning our time at 10:15, and then it's gone silent. Right, and it won't come back up. Sadly, they didn't actually put it on a plaque. I thought it would have been a nice touch to have it on a plaque there rather than just broadcast it back to mission control, so that future people, as they're walking around on the moon, could come up to this historic marker and see what was written at the time. All right, so tonight, welcome everybody. We've had a number of new members since we last met. We've had David Barnes, Karima Potemkin, Jerome Asso, and family. Any of those here tonight? No? Okay, fantastic. Welcome to the Society. I'll now go through the events of the past month and coming month. Chris isn't here yet, so I'm not sure when he's going to roll on, so we might skip over his until he comes along. So it may very well be Guido first. Then we'll look at something completely different, the secret life of a snowflake that is given by a solar astronomer, which seems to be something completely different from what you might expect in terms of temperature. Then we'll close with landing on the Saturn's large moon Titan. All right, recent events, and we've had plenty of them. Been a very, very busy month. So these couple of photos here were taken by Phil Peters. There was one, the top right is at Bentley Street Festival on Centre Row. We had around about 1,700 visitors and patchy cloud and a bit of rain in that during the day, but overall it was clear, as you can see from the shadows on the pavement there and on the road. Then we had St Mary's Catholic School here. And the committee meeting. Parkdale Secondary, which is always a very big night, lots of people there and lots of very interested kids. That went very well. No cloud, fortunately. They've been clouded out the last couple of years that we've done them, but this one, fortunately, they had plenty there. And they were able to see everything up in the sky before clouds came in later in the evening. Then the public night had Manfred Berger talking to the public, and again that was clear with no cloud. Then the bottom right picture of Somerville Family Day, or the Family Fun Day as it used to be called. We had over 3,000 people visit us. The total count was over 10,000, so we had roughly a third people actually stop at the tent and have a look, rather than just sort of wandering on by. Then a couple of days later we had Strathayde Primary here, who were at camp next door in the Briars, and that was generally a good evening, a bit cloudy, but you can't do much about the cloud on the evening. And then the cosmology group on the Saturday was here at the Briars, and they had slightly reduced number present for that one, 14, but nevertheless a really good turnout. So coming up soon, we've got this Friday and Saturday in Inverloch, a public night being done in collaboration with the ASV and I think also the tourism body out that way. Is that right, Dave?
Inverloch. It's the Inverloch Equinox Festival.
Inverloch Equinox Festival. There we go. Very, very Stonehenge-y. Yeah. So we've got a couple of members going along to actually help that one, given that's a fairly long range away. This Saturday we've got the Telescope Learning Day here at the Briars, and we're trying out a buy-sell swap because a number of members had actually asked us to give that a go. The Telescope Learning Day starts at 4 o'clock, and I imagine the playing with the telescopes and haggling over telescope parts and bits and pieces will probably start an hour or two before that time as people sort of wander in. We've got plenty of trestle tables that we'll put outside for that sort of thing. And really, if you only really needed to book if you were staying around for the food a little bit later on. So if you haven't booked and you wanted to come just for the telescopes and that, I would say just turn up. It won't be that important. And Guido will be giving at least one, if not two, talks during that evening, like last year. Committee meeting is on the 25th, which is the Tuesday, I think. Then. We've currently got no bookings for the Scout Cubs and Guides night that Friday on the 28th of March. If it's a couple of days beforehand and we don't have any bookings, we'll cancel that one, and they'll have to wait until the next one we run about 3 months later.
The planned start party is Border 1 Skies up at Echo Bend Caravan Park, which is up at Glenadale.
Yeah, that one.
So it's about 3.5 hours drive or so into the east. We're looking to try and get another 10 or so people there, make it about 50. So it should be a good event.
And is that a different location to the last time it was held? It is a different location.
A little bit closer, actually, half an hour closer.
Yeah, half an hour closer.
I think it starts on the 28th, the same as that Scout night. So a lot of the key people won't be here for that Scout night, so it might be a good idea to scrub that anyway.
Yeah, I suspect at this late stage, because we only opened up bookings last night, that we may not get any in time. So we have had inquiries from a Scout group today, but I don't think that they will go that soon. It's just not enough forewarning for them to get their numbers together. Public stargazing night at the Briars on 4th of April is already booked out. Not sure whether Manfred is going to be able to talk at that one, so he's penciled in at the moment, but it promises to be a full one, so we got a lot of people booked in there. 11th of April, we've got a church youth group here. I'm not sure if it was meant to be Red Hill Church Youth Group, but that was the name that they gave us for the booking. They're staying, I think, next door at the Briars camp, and then coming over a little bit later. And then after the next meeting, we have the next cosmology group meeting here at the Briars. So there's not in the next month the cosmology group meeting, it's in the following month. And of course, just a reminder, you've got the astronaut Chris Hadfield in Melbourne here at 1st of July.
Welcome to AstroMofo. Here we go. So our last challenge was Puppis, constellation of Puppis in Argo Navis. We've got some really good photos this year, this challenge, and a couple of new members have also contributed. So this one here is from Mark Schapper, and it's a cometary globule CG30 with his home set up at his place using a really nice telescope and camera combination. And he's managed to capture this image with about 6 hours of exposure on a RGB, so monochrome camera, luminance, red, green and blue filters. So cometary globules are concentrations of cold, dusty material. They've got very dark heads, as you can see, and we're getting a bit of star formation. So in the cometary globule there on the right here, you can see that little bright spot in the middle. That's probably a new star that's forming in that area there. So in this photo here, CG30 is on the right, and CG30 is on the right of the larger one, which is CG31. What else is there about this? So they're about 1,300 light years away. The field of view on this image is about 1 degree by 1 degree, so about 2 moon diameters by 2 moon diameters. And we'll just have a look on where it is. We'll have a look at where it is later, but this is the showing where Puppis is. So that's the constellation of Puppis right there. Vela was the previous challenge, right around here. And where that is relative to a few other things, you can see Canis Major here, and you've got the tail and the hind legs of the dog. Columba there, and then you've also got Carina down the bottom over here. So this is the region here where we're imaging and when we're looking at objects. Okay, and CG30, if we have a closer look at Puppis here, so in this image, that's where the cometary globules were in the previous image. So you've got Canopus over here on the left, and down here you've got Canis Major on the bottom of the screen there, and Puppis in the middle, and that's where we've got these cometary globules. Okay, this challenge was completed by Mark Schapper, whose image we just saw then. Michael Barrow, David Rolfe, Sylvie Grandit, Greg Walton, Nick Axaris, and yours truly. And this is a photo from Michael Barrow, so it's a first image from Michael as well. And this is taken with his sea star, NGC 2467, which is the Skull and Crossbones Nebula, and is taken about 432 10-second shots to collect this image. So well done, Michael. This one here is pretty much a wide field shot showing everything from the Eta Carina Nebula on the left all the way across to the tail and hind legs of Canis Major on the right. This was taken with a 20mm lens and my Astro camera, so fairly wide field of view there, spanning a fair chunk of the sky. And this was taken with the Antilla tri-band filter, so it filters out a lot of the light pollution and lets us see a lot of the nebulosity in the stars. We've got Eta Carina Nebula on the left over here. We've got the Gum Nebula in the middle over here, and then on the right, like I said, the hind legs and the tail of Canis Major. And pretty much in this shot here, we've got Puppis in this area and Vela in this area on the left of the screen, and then across the bottom is Carina, the hull or the keel of the Argo Navis. Canopus is pretty much just at the bottom of it's out of the field of view, so I wasn't able to get all of Carina in this field of view, but I'll try again next time. This, I had the lens set at 20 millimeters for this shot. If I zoom out a little bit and make it 14, I might be able to get the whole thing, so we'll give it another go. And this is the field of view looking, this is from Stellarium, so this is the field of view in the red rectangle of what was in that image there. And okay, we'll have a look. We saw the C-star image of the Skull and Crossbones Nebula earlier, and this is where the Skull and Crossbones Nebula is in Puppis. So it's up towards this part of the deck. And what I learnt was Puppis, or the poop deck, what it actually means, it's the rear of the ship, and it's generally a covered area of the ship where the navigator or the officers meet to chart navigation and discuss official discussions, have dinner and whatever else. So it's got nothing to do with pooping off the ship. Yeah, it's generally the covered area at the back and where all the navigation and steering happens. Okay, Skull and Crossbones imaged by me, and we had some really good nights a couple of weeks ago, so I was able to set up the telescope, and which a few members did, I think, and get some pretty nice images. And this one is 51 by 5 minute exposures, so about 255 minutes in total of the Skull and Crossbones Nebula using a couple of filters. And what the filters do is they just cut out all of the light pollution and just focus on the light that's coming from the nebula. So the tri-band filter does that. The L Extreme is a dual band filter. It captures the hydrogen alpha and the O3 emissions from the nebulas. So the two, I find using a combination of these two creates some pretty nice images. So the Skull and Crossbones is a star-forming region. It's around about 4,400 light years away, and there's a fair bit of star formation going on over there. This one is by Nick Axaris. He calls it the Cleopatra Nebula, and I can see why, because it looks more like a lady with a headdress rather than a Skull and Crossbones in that orientation anyway. Yeah, a bit of evil red eye going on over there, so I don't know, maybe she's caught her husband doing something he wasn't supposed to. And this one here by Sylvie Grandit with ASI 2600 camera and 115mm triplet reflector. So all these three images of the Skull and Crossbones were with refractors. Sylvie's is with 115mm refractor. This one is with 130mm refractor, so it's a longer focal length, so it's a more zoomed in image. There's a bit of cropping going on as well, and this one is with an 80mm refractor, so a wider field of view again, so it shows the difference between the telescopes. The 130mm is able to capture a lot more detail in the image, and there's probably a bit more skill with Nick and doing a bit better processing and capturing the details, but generally the wider the telescope, the more detail you'll be able to capture. Dave captured this, we've got some open clusters coming up. So NGC 2451, captured by Dave Rolfe with a monochrome camera and HAO3 and luminance filters. So hydrogen emission and O3 light captured by Dave, and he's managed to capture some of the hydrogen alpha emissions, which you can see the pink light around that nebula there as well. And this is the Stinging Scorpion cluster, which is actually two clusters, one in front of the other. So they're generally called NGC 2451A, which is the closer one, and 2451B, which is the further away one, but they're in the same line of sight. So one is about 600 light years away, and the other one is about 1,200 light years away. And that's where that is situated in Puppis, right up near the star where it joins onto the Carina and Vela, the sail. That's this field of view, and I've orientated that way because there's two clusters there which are actually pretty close together, and that is them there. So we've got the Stinging Scorpion on the top right. This one is imaged by me. Stinging Scorpion up in the top right, and in the bottom left is another nebula called the termite. What's it called? Termite hole, the termite hole, or the electric guitar cluster. I don't know why it's the electric guitar cluster, but this has been described as one of the nicest open clusters to look at, and it is sort of being compared to a globular cluster, but without the dense core, and it's actually quite apparently I haven't actually spotted it with visually, but I'll definitely give it a go because it is apparently it's a very nice one to have a look at through a telescope. Okay, so that one there's approximately 300 stars in that one there, and it's estimated to be about 2,000 light years away. Now I've got a couple of photos by Greg as well. So this one here is, Greg's always good enough to put the information on his images so I don't have to write it down, but M46, that's imaged here with the Meade telescope and Canon camera, and that's it's only 7 shots at 30 by seconds, at 30 seconds long each. So he's captured a nice image of this cluster, and as you can see there's also a planetary nebula in there as well. So planetary nebula is a star, a solar mass star up to about 8 solar masses, which has come to the end of its life, blown off its outer layers and forms what's called a planetary nebula. And planetary nebulas don't actually last very long in the sky compared to the other things we look at. They're there for about 10 to 20,000 years before their gases dissipate, and in the middle of that is what we call a white dwarf. So the open cluster here is around about 5,000 light years away and contains about 500 stars, and the planetary nebula is much closer at only about 1,300 light years away. And this is M46. There's also another Messier object, M47, close to that as well. So in the field of view here, it's just sort of, it's outside of the stars that make up Puppis, but it's within the constellation boundary, just in this section here near Monoceros and Canis Major, just in that corner there. And this is M47 by Greg, so the other cluster of the pair, just next to it. But I think Greg snuck this one in because it was 5th of March 2011, which I just noticed after I put it in. So not really eligible. This is supposed to have been taken within the time constraints of the challenge, but I let it pass because it's a pretty nice shot. And that's a recent one taken by Greg as well with the Meade from here as well. So this is eligible. It was taken within the time frame. And this one here, M47, was actually called the Lost Cluster. It was a lost cluster. Messier catalogued it. He wasn't the first to catalogue it, but he did catalogue it in his list of Messier objects. But when someone went back to have a look at it, it wasn't where he had noted it to be. But then someone realised that he had mixed up a plus and a minus sign on his right ascension and declination notations. And when you switch the plus and the minus and look there, it is there. So even Messier made a mistake. Okay, now this is part of the Gum Nebula, the big red structure that we saw in the first image. This is looking at a very small part of it with my telescope. So this is around about 6 hours of imaging with the filters again, and my 80mm refractor. And it's basically the Gum Nebula is a glowing cloud of hydrogen gas emitting hydrogen alpha emissions, so ionized hydrogen. And it is in that part of the Gum Nebula that you see in the middle. Up on the top right, I've also noted where the Skull and Crossbones Nebula is too, but that little section there is that image there. So 400mm focal length, 20mm focal length. Okay, and now the next challenge that we're doing will be Carina, the Carina Nebula down the bottom. So we can see from the constellation here again, we've done Vela, we've done Puppis, and the next one is Carina. So any object, and there's a whole heap of objects that we can image and have a look at in Carina, either with telescopes or with wide field cameras or anything like that. We've got some really nice objects. Now I think there's a slide missing here. Bear with me for a second. Where am I? Oh, don't worry about it. The leaderboard. Okay, so what I've decided to do is just keep track of all the submissions that we've had so far this year of people submitting photos. So going from January, this is everyone who submitted a photo and in which month they've managed to submit it. So we're going to keep score through this year. And it's not about who gets the best shot, it's about who gets a shot. The idea is to get out there and pull your camera out and have a look and learn about what we're imaging. So a bit of a scoreboard, and you never know, nothing official, but I might try organise something for the Christmas party to whoever manages to capture the most shots of most of the months. There we go. That was AstroMofo. Any questions? The new challenge, March to April 2025, Carina, and the details on where your images can be submitted. Okay, thanks very much.
All right, so let's have a look at the sky for the rest of March and the first half of April, starting with Nick's fantastic photo here of, I think, the Pencil Nebula. So here's a look at the solar system kind of seen from the top. We can see, let me just get a pointer here. We can see Earth around here in relation to the Sun, and you can already see that both Venus and Mercury are very close to the Sun, so we won't see much of those two. And Mars is now well past opposition, but still nicely positioned in the night sky. So if we go through the next month or so, so this is for tonight, we can see how the planets will move over the next month or so. And as you can see, Venus and Mercury both passing between Earth and the Sun. So when we zoom out, we see the outer planets around here. So Jupiter's still visible, right? So if we look from Earth, then basically this is the direction of the sunset, right? So seen from here. So Jupiter is still relatively high in the sky, just around sunset. So we still have a few hours. Saturn now on the other side of the Sun, as well as Neptune. And Uranus setting just before Jupiter, right? If you draw a line from here, you can see Uranus will set a little bit earlier. So looking at that through kind of an all-sky perspective from the Briars, this is around 7 p.m. on the 1st of April now. So in terms of where we are with the Earth and the Sun, sunset is around 7:15 now. We have the equinox coming up tomorrow and the end of daylight saving time on the 5th of April. I think lots of astronomers are looking forward to that, to getting a bit more night back. So the moon for the next month, we will have the next new moon on the 29th of March, and then the full moon on the 13th of April, and the April new moon on the 28th. The new moon on the 29th, of course, just in time for the Gippsland Star Party as well. So we should have nice and dark skies there. Looking at some of the other planets, well, the only ones that are actually visible, Uranus now very low in the sky, setting just after sunset, really, and heading towards its conjunction with the Sun when it will disappear behind the Sun. Jupiter still pretty bright at the moment, around second magnitude, but now sets just after 10 p.m., or at least around the 1st of April will set just after 10 p.m. And Mars then following a few hours later around 1 a.m., but still observable at the moment, although you can see that it's relatively low in the kind of the northern sky there. So if we go forward to around 10 p.m. and just have a look at the major stars in the sky for the moment, we can see Orion with Betelgeuse and Rigel here already now setting, well, maybe around 11 p.m. or so, so clearly heading into winter. Around 10 p.m. we have the Southern Cross now a lot higher again than last month, and the Milky Way starting to really stretch across the sky there. And looking at the major constellations, yes, I just mentioned Orion here, and then we have all the constellations of the Milky Way just across the sky at the moment. So we we're not quite back to winter, but definitely with Orion setting earlier now, heading that way. There's not much else really to say about the rest of the night. So we have all the major targets that we've had for the last month as well. And yeah, most of the planets are really disappearing now. So heading towards the early morning, we will see that Saturn is now actually reappearing from behind the sun. Probably still have to wait a few seconds. So yeah, there you can see just before sunrise, we can see Venus, Mercury, Saturn, and Neptune kind of clustered around that part of the sky there. So they should be visible just before sunrise. And then sunrise is around 7:30 a.m. Venus is heading towards inferior conjunction, so when it is between the Earth and the Sun on the 23rd of March, so just in a few days, and then returning to the morning skies in April. Mercury is observable in the morning, so it's already past its inferior conjunction. And it will be only 2 degrees from Saturn around mid-April. Saturn also passed its conjunction now, well, at least on the 1st of April it will be past conjunction, and then rising early morning around 6 a.m. and a little bit later, rising a little bit earlier towards the end of the month. And the rings are now completely edge on at the moment. So if you get up early and you catch Saturn just before sunrise, that might be a really interesting opportunity to take a photo with the rings basically completely disappearing at the moment. But it'll be tricky because it's still quite close to the sun. And finally, Neptune is in conjunction with the sun tomorrow. And then it'll become an early morning object after that. The apparent sizes of the planets on the 1st of April, you can see Venus there, in the bottom left, appearing absolutely massive, but that's because it's very close to us and between us and the sun, so we can't actually see it at that size. And we really see Mars shrinking very quickly now over the next few months, and Jupiter also quite a lot smaller than it was just a few months ago. And yeah, that's pretty much it, because don't have any comets brighter than magnitude 10. We don't have any meteor showers coming up until I think later in April. So yeah, I think it was a pretty short one, but there's still, I guess, enough to see with at least the Milky Way being up and some of the planets still there. So sources, as always, Stellarium, NASA, Eyes on the Solar System, and the Astronomy 2025 Almanac. That's it. Thanks.
This one was given by Professor Ken Libbrecht from Caltech in the USA, and that's a picture of him there. He's famous for macro photography of snowflakes, including so-called stellar snowflakes. He's a solar astronomer from what he did his PhD in at Princeton University, but he's made his fortune selling books on ice and snow and things of that nature. The structure of snowflakes. He was the main science consultant for the movie Frozen, as you can imagine, shown there, and US and Swedish stamps shown on the right there feature his work that he's captured. He actually lives in California, which tends to be a bit warm for snowflakes, but interestingly, no one else is studying them in the colder climates. So this public lecture was recorded in 2012, and it goes for about 1 hour, just under 1 hour.
So now please join me in welcoming Professor Libbrecht as he reveals the secrets of snowflakes. Professor?
Hey. Perfect. Okay, thank you everyone, and welcome. So, what I want to talk about tonight is snow. okay? A familiar subject, maybe not so much right now, but it's a familiar subject. But I want to take a close look at snow, and we're going to really get in and not look at snow as a pile of crystals, but we're going to look at individual crystals. We're going to zoom right in and look at individual snowflakes, okay? What are we going to do? Well, here's some. These are, you've seen these two icons of winter holidays. These are photographs of real snowflakes. And things like this you see on wrapping paper and all sorts of things. But let's take a close look at one of these. So here's a snowflake, a photograph of a real snowflake. And so what I want you to do tonight is just take a close look at this, and we'll sort of see what we can see. Like you might notice, for example, if you look carefully, that this branch is parallel to that branch, which is parallel to this one and this one. And similarly, there's a lot of horizontal branches. So there's a lot going on. The crystal forms with these parallel branches. And so that tells you something about why the crystal has that structure. And we'll be looking into that. Okay? And we can look really close. We can start to really get down into the insides of the snowflake and try to see what makes these guys tick. Okay, so let's start at the beginning. Let's take your standard snowflake. And what I want to look at is, why does it have this shape? Why does it look like this? It could be any shape. Why this shape? It has a certain symmetry. As you can see, there's branching and side branching. There are facets on these crystals. Why is all this happening? Well, if you want to ask why the crystal looks like this, you have to ask kind of where it came from, how it was made. And so that's the first step, is to just ask, how are these crystals being formed? Okay, so let's take a look. All right, here's the wrong way to make a snowflake. Okay. So here when people make things, we make things in factories. We manufacture, right? And so there are drawings, and there's a factory, and there's you start with raw materials and you make things. And when you do it that way, everything looks the same. You make cars, they all look the same. But nature, nothing is made this way in nature. Nature, when you make a tree, you don't get a plant and start with wood. No, you plant a seed and it sort of turns into a tree. In nature, things grow. And when they grow, they're sort of forming by self-assembly. And this is what crystals do. Snow crystals do too. They grow. That's one reason they all look different. I mean, they're growing, and so it's sort of a somewhat random process, okay? So that's the wrong way to do it. What's the right way to do it? Well, let's start at the beginning again. We'll go back and say, where does the snow come from? So here we have snow on the ground, and where's it come from? Well, it came from the clouds. So what's happening up in the clouds? Clouds are made of water vapor, clouds are made of water droplets. Okay, lots of little tiny water droplets floating in the air. And as the cloud gets colder, the droplets start to freeze. They don't all freeze at once. So there's one. Let's say, look at that one. Say that freezes. What happens to it? Well, it starts to grow. It's accumulating water vapor from around it, and the water vapor lands on the ice, and the ice starts to grow, and it gets bigger. Where does the water vapor come from? It comes from the droplets. The droplets will evaporate, and so they evaporate and turn into water vapor, and then the vapor condenses on the snowflake. Okay, and it takes about 100,000 water droplets to make one snowflake, and eventually they get heavy enough that they fall. So this is how you freeze a cloud. I mean, you start with liquid water in the form of droplets, and you end up with solid ice. It's really a lot more complicated than you'd think it'd have to be, but that's the way it works, okay? So now let's take a closer look now at what's going on in the crystal, okay? So there's an ice crystal. We know how the molecules fit together in an ice crystal. Crystal means that the molecules are all stacked up in a nice orderly way, and there's a picture of the ice crystal. And if you wait like now, you see it has this six-fold symmetry, okay? And that's just the way the molecules are hooked up. Why do they hook up that way? Well, now you're getting into chemistry and quantum mechanics, and we're not going to talk about that. This is just the way they hook up, okay? Not all molecules hook up this way. There are lots of different crystals. Some of them are square and different patterns, okay? But this is the way it works with ice. And so when this crystal is growing, say you start out with a little round piece of ice, the molecules are all stacked up, and the molecules are hitting. It's growing, and so the molecules are hitting, and the facet surfaces are nice and flat, and there's not a lot to hang on to. There's not a lot of molecular binding there. Whereas these rough regions, those little nooks and crannies, there's lots of molecular bonds available. And so the water molecules like to go to those places where there's a lot of chemical energy. And so they go to the bonds, and so the rough regions soon fill in if you let it grow. And so as it fills in, it starts to form a faceted crystal. And so if you start with a round crystal and let it grow for a little while, the fast-growing surfaces grow and the slow-growing surfaces don't, so pretty soon you're left with nothing but slow-growing surfaces, and those are the facet surfaces. Okay, and so this process is how the geometry of the water molecule, because it has some geometry, and that's how it's transferred to the geometry of a large crystal through this process of faceting and the sort of selective growth of different surfaces. And when we grow little tiny crystals in the lab, we get these little hexagonal prisms, so that's how it works. And this also tells you why there's no four-sided snowflakes or 5 or 7 or 8. Okay, you may cut those out of paper, but in practice, in nature, there's only 6-sided snowflakes, and it's because of the underlying structure of the crystal. Okay, so now what happens? Okay, the snowflake gets larger, and it'll undergo this thing called a growth instability. I would call it a branching instability. And what it is, you've got a hexagon over here, and the water molecules have to sort of diffuse through the air to get to it. Okay, there's a lot of water out here, not so much near the crystal because it's kind of sucking all the water out of the air. And so the water molecules are drifting in, and the corners stick out a little farther. And so since they stick out a little farther into the humid air, they grow a little faster. Okay, so the corners grow a little faster. And then there's this instability. It's a positive feedback. What happens is they stick out a little bit, so they grow faster. Well, that makes them stick out even more, so they grow even faster, and they stick out more, and et cetera. And so if you start with a hexagon, pretty soon you can sprout branches. And so when this process starts, it takes off pretty fast, okay, because of this positive feedback. And that's a growth instability, this positive feedback. And then you get a branched crystal, and then with time, you can see it can make side branches also, okay? And this is how the snowflakes get most of their structure, through this process of branching and side branching, okay? So here's sort of the picture, a scene from the cloud or from the snowflake. Just to summarize, you start with a little water droplet, it freezes, it grows into a hexagon because of faceting. As the hexagon gets bigger, then it starts to form branches, okay? And branches will all form at once because when the conditions are right, they all form at once. And the crystal then changes, it's falling through the cloud, so it'll see different humidities and different temperatures as it falls. And each time it sees a different set of conditions, the growth changes. And so for a while you get branching, and then maybe you get plates growing on the ends of the branches, and then more branching. And so it goes as the crystal falls. And so now the crystal, if you look at it, it had a complex history. Okay, the temperature and humidity it saw as it fell is just a very complex function. But each arm saw the same history because they all traveled together. When they were over here, one temperature, one over here. So they all grow in synchrony. The 6 branches all grow in synchrony. So it has the symmetry. And no 2 crystals follow exactly the same path, and therefore they all look different. So you have these crystals that are symmetrical and yet different from all the others. Okay, and it's just because of this sort of set of conditions. Okay, so when you look at a snowflake now, here's a nice example of a nice snowflake. You can see the basic features. Okay, there's a little hexagon right there. That's how it started, with its little faceted hexagon, and then it sprouted branches. And then it started maybe side branches, and the side branch, there were these side branching events where side branches formed on all 6 arms at the same time. And so it goes. And so it has this symmetry. It's not perfect. And so you can also see why the branches are parallel, because the directions that the arms grow in has to do with the underlying crystal symmetry. And this is a single crystal, so the molecules are all lined up in here from one end to the other. It's a complicated shape, but inside the molecules are all lined up in the same direction. Okay? So it's great. There it is. You can sort of understand, in a nutshell, how snowflakes form. Okay? But what if you see this on your sleeve? That's something weird. Or this. You might find this on your sleeve one day. Or this. What is that anyway? Okay. Well, these are all snow crystals, in that each one of these is a single crystal of ice, just like this one. This is a single crystal of ice. All of these, they're different kinds of snow crystals. Now, you don't see these other ones. At Christmas time, you only see these. These have good press agents. The other ones, no, they're sort of the black sheep of the family. So we want to understand, how all these things work. Why do we get all these different types of crystals? Well, one of the fun parts about science is everything's connected. Okay, everything's interconnected. So if you want to figure out how a snowflake forms, you start to look at other crystals. So, for example, I started reading about this subject because I just got interested in it. And there are mineral crystals, rocks. Minerals are crystals. There's thousands of different minerals. You can get rock hounds can go out and find different crystals. Here's just a few examples. And geologists study these things. They like to know what's in the ground. And you can get the crystal structure of all these minerals from crystallography. That gives you where the molecules sit. That's sort of a statics problem. That tells you where the molecules are in the crystal, just like the ice crystal diagram I showed you. We know where the molecules sit in these crystals, but they also grow into these funny morphologies, and we don't really know how this works. And you talk to the geologists, and they don't actually know how this goes. And as people try to model it with fancy computer models and things, molecular dynamic simulations, and that doesn't really work either. So again, when you start researching this and reading about this, you find that people just don't know this. We dig these minerals out of the ground, and we don't really understand why they look like they do. And that's true for most crystals, including ice. Ice is a mineral, and we don't quite understand why they have all these complicated shapes. It's a puzzle. Well, what about industrial crystals? There are a lot of crystals we use, like semiconductors. Okay, every computer and every cell phone begins with a block of semiconductor, and so we grow lots of semiconductor crystals. Surely we understand everything about this. So I started reading about this, and no, not really. We don't really understand this either. What the engineers do, the engineers want to make big, perfect crystals, and they develop these recipes for how to do it. It's just like cooking, you develop a recipe. Even if you don't know exactly what's going on with the recipe, you know how to do it. And so that's kind of what happens, is all these crystals people make, they don't exactly understand how they work. It's just you've developed recipes over the years that do work, and if all you care about is the final product, you know how to make the final product. We obviously know how to make semiconductor crystals, but the fundamental physics of it, the molecular dynamics, is still puzzling. And so again, we don't really understand how these morphologies come about, and we can't calculate growth rates and things like that. And so it's it's a bit of a puzzle. And when I got started in all this, I wasn't thinking about ice exactly. I was really thinking about crystals in general, including important crystals, semiconductor crystals, and diamond crystals, and thinking about, well, how could you make these things better? What else can you do? If you understand the physics better, presumably you can understand how to make better recipes and make better things. But it's a hard problem, because crystal growth is very molecular dynamics, involves a lot of molecular dynamics. It's complicated stuff. And so when I was looking about this, I was thinking, well, it's the broad problem is really too hard. So we want a simple, you want something you can get your hands around. So it's like, well, what you need is a case study. So let's pick one crystal and figure out how that one works, okay? And don't worry about the rest. Don't worry what it's good for. Let's just get one, and we'll get that. So which one? And it's like, well, there's this. It's like, wait a minute. Ice. Ice is the perfect one. Why? Why is ice great? Well, it's a simple system. It's just one molecule, water. We really know about that water molecule, too. I mean, people have studied water for a long time. We all know all about the chemistry and everything. These things grow from vapor, and that's convenient. We understand vapors really well. It obviously has a lot of different shapes. Now, as an experimentalist, I really like these next two. It's inexpensive, and there are no safety issues. I've grown other crystals as well, and trying to understand crystal growth. And every other crystal you can sort of think of growing comes with a lot of safety baggage. You have to you buy these things, you have to dispose of them, you have to not ingest them. Not water. When you're done with the experiment, you pour it down the drain. You can't pour anything down the drain anymore, but you can pour water, so it's a great crystal. So now we're trying to understand the molecular dynamics of how crystals grow by looking at this one, okay? So there we go. How do we start? Let's do a little experiment, okay? Because one thing, nice thing about ice is you can do some experiments with it. It's cheap. So we have a tank, and the tank is maybe half as tall as it is here, about 1 meter high. And we put some cooling pipes around it so we can chill that tank to whatever temperature we want. It's got air in it. And then we put some heated water inside the tank. And the water evaporates and puts water vapor into the air. And that floats around here and cools. And so now you've got a lot of water vapor and cold air, so the air becomes supersaturated. It means the humidity is above 100%, so crystals can grow. And then we have a little nucleator. You've got to get the crystal started. And what we do is we take a little pulse of compressed gas, and that expands very rapidly. It gets very cold, and that causes crystals to form. So we nucleate a bunch of little crystals, and then they just float around here, and they're very tiny. They float around and grow until they eventually get heavy and they fall. and we have a microscope down here. So it's a lot like what happens in the clouds, except it's a really tiny little cloud. Okay, and so they don't fall very far, they don't get very big, but we can see what happens when we change the conditions. So let's do that. Here are some crystals made that way. These are grown at -2 Celsius, okay, just below freezing. And what do you see? Here's a 50 microns, so that's very small. 50 microns is about the diameter of a human hair. Okay, so these are tiny little crystals because they didn't fall very far. And mostly these are little plate-like crystals, okay, little hexagons. There's a lot of variation because the conditions in the tank are not super constant, but mostly they're little plates, okay? So let's do the experiment again, but now at a little colder temperature. Here's -5. So instead of plates, we have columns. So think wooden pencils. You know, they got 6 sides and they're long and skinny. Well, that's what these are. They're long and skinny and they got 6 sides, okay? And so you see it's very different just by changing the temperature. And then we can go a little colder, -15, okay? And now we get plates again, but big, thin plates. Here's one seen edge on. They're very thin. So again, the morphology changes just with temperature. So we can put all that together. We can do the same experiment over and over again with different conditions, and we get what's called the snow crystal morphology diagram, okay? And what it is there's temperature down below and humidity over here, or supersaturation. And so if you grow crystals at very low supersaturation, that means they grow very slowly. And so then you get simple things, simple prisms. Okay? As you grow faster, they grow faster, they get more complicated. Okay, that's the way these things usually work. But we sort of understand that. But they also switch. They go from plates to columns to plates to columns, okay, as a function of temperature. And that's kind of a strange behavior. This was discovered a long time ago in the 1930s by a physicist, a Japanese physicist, Ukehiro Nakaya. He was the first person to do these experiments, and this is what he found. And what's really amazing is we still don't know why they do this. I mean, here it is. We don't even have a good qualitative explanation. It's not like we're missing a few details. It's we don't really know at all. And it's just ice. You'd think we'd understand everything about ice. It's, snowflakes, they fall out of the sky. But this thing where they change with temperature, we don't get that yet. So that's a puzzle. It's a great puzzle. We're trying to understand this. Okay, this line, the water saturation line, that's sort of the supersaturation you might find in a dense cloud. So these are sort of atmospheric conditions. Okay. So what do we do? How do we solve this one? Well, one thing we can do is go looking around. First step in any scientific investigations, you got to do some observations. And so I got into snowflake photography. It's a funny thing to do, but I do it. So what I do is start with a microscope. I made my own microscope. Snowflakes are sort of the wrong size. They're a little too small for macro lenses. They're a little too big for a microscope. So I made something that fits the size of the snowflake. And so I go out and look for snowflakes. I should point out, though, that you don't need a lot of fancy equipment if you want to look at snowflakes. What I like to do is I carry one of these around. That's a little hand magnifier. Costs a couple dollars. And you can see a lot of neat stuff if you just put that and point that at your snowflake sometime. Okay, so I recommend you might want to go and look at these things. All right, so here's how it works when photographing snowflakes out in the field. So you can't just pick up snow on the ground because when the snowflakes sit on the ground, they sort of deteriorate and they don't look so nice. You got to get them right when they're growing or soon after they've grown. And so what I do is you wait till it snows, and I set out a piece of cardboard. That's that blue cardboard. It's right over here on a tripod. That's just a piece of blue cardboard. And you let the crystals fall, and this is what I do anyway. I let the crystals fall. And then I look around. Here's the cardboard you see on the edge here. And I look around for nice crystals. It's like, well, that's a piece of junk, and so that one might be good. And so then when I see a good one, I pick it up. I got a little paintbrush, and I just go in there and you kind of pick it up with a paintbrush, and you put it on the microscope slide and stick it under the microscope. So there you go. And voila, nice picture of a snowflake. Repeat. Okay. People ask, you're picking these things up, aren't they little tiny and awfully fragile, and what if you break them? It's like, yeah, I break them, You just throw it away, Nobody has to know. They're falling out of the sky, so you break one, the wind blows them away, you just pick up another one, try it again. So What about, do they melt? People ask me something, do they melt? I mean, you're putting them under a microscope. And yes, they do. And if it's cold, then it's like on top here. They don't melt, they evaporate. So this crystal is sitting under the microscope, and I have to have some light on it. So I have the light put some heat into it. And also my body is a little warmer. And so they start to deteriorate. And so about 2 minutes, you see this one I just let it sit on the microscope slide, and I took a picture and took another picture and another picture. And after 2 minutes, there wasn't much left. And so, and that's the norm. I mean, you got to be fast because they do deteriorate, they evaporate. Sometimes, if the weather's warmer, this top one is about -15. It was outside. Here is -2. Okay, it's very warm. And so when it's that warm, they evaporate a little and then they just melt. And so it turned into a little puddle. It's really hard, even 27 seconds too. You really got to rush with these. It's a lot easier to take pictures of snowflakes when it's colder. Okay, so if you want one like this, you got to be in the right conditions. Got to be cold. You got to hurry and you got to jump in there. But you have to do that anyway because you need a lot of pictures to get some good ones, and so you can't sort of dilly-dally around. You just got to throw them in there one after another because the snow only falls so long. Every snowstorm is a little different. Sometimes you get lousy snow, sometimes you get great snow, and the crystals change from about 15 minutes, and they can change a lot. You get good at this picking up snowflakes. Here I picked 5 up and put them all on my microscope slide, so made a little snowflake family portrait. So there's that. You can really find some beautiful ones. I mean, if you go out and look for these things and spend a lot of time at it, which I do, it's really fun. I like to take pictures of snowflakes. It's like a treasure hunt. You never quite know what you're going to find because they're so tiny, you don't really see it until you put them under the microscope, and then it's like, whoa, that's a great one. And now, I have to point out, full disclosure, that this is usually what you see. If you go out, next time it snows here in Waterloo, you get out your magnifier, 90% chance you'll see this, because this is the normal thing. And what this is, it's just a bunch of little tiny crystals. They're all forming really fast, and they collide, and they stick together, and you just get a mess, and they all interfere with one another's growth. This is the wrong kind of thing. What you like is a day when it's cold and when the crystals are falling or coming down very gently, slowly, not much snow, not a snowstorm, no wind. Okay, so so you can get some nice crystals. Now, if you want to find some of these beauties, these big ones, you got to be really in the right place at the right time. Not any old snowfall is going to give you a nice snowflake. There's maybe a few, but not very many. Okay, so you really got to be, like I say, in the right location and at the right time. For example, where I live, Southern California. Okay, this is not a good place. So. That's where I live, but it's funny. I live in California and I photograph snowflakes. Go figure. So I take my show on the road. That whole microscope fits inside a suitcase. One of the real challenges is getting that sucker through airport security. So I'll go to places like here's the Michigan Upper Peninsula. That's not too bad. I've taken some nice pictures there. Of course, you can't have too much of a good thing, and. I always say it's hard to appreciate the beauty of a snowflake when you have a shovel in your hands. So, I spent a little time up in Alaska. Cold place. That's like going to another planet, one that's far from the sun. This was noon in Alaska. You see how high the sun is. And it was often 40 below. That's too cold. 40 below is too cold. There's not very many snowflakes at 40 below. Up in northern Sweden, got some nice pictures up there. I get invited places. I go these places. In Japan, there's really beautiful snowflakes in Japan. It's funny, if you live in a cold climate, you take your family down to the beach for vacation. What do you do when you live near the beach? I take my family to snowy places. It's just a crazy world, but they like the snow. My favorite spot for photographing snowflakes is right here in Ontario, in Cochrane. If you don't know where Cochrane is, it's about 700 kilometers north. Just drive until you run out of road, and that's Cochrane. And it's not a big town; it's a little town, but it's really got just the right conditions. And we know this from the morphology diagram because you can sort of see where the best crystals grow. They grow around -15. See, so I'm looking for a place that's got that's the temperature normally. Light snowfalls, heavy snowfalls are bad. Light is good, and no wind. The wind breaks everything up. So this is a great place. Like I say, I've been to Cochrane many times to photograph snowflakes. And here's some examples. I get some pretty pictures. What else? Just snowflakes, really very spectacular things. Let's see, you may be asking about the color. These are very colorful pictures. Why do snowflakes, aren't snowflakes supposed to be white? Not really. Snowflakes are actually clear. After all, it's just a sliver of ice, and ice is clear. And so they look white on your sleeve, the same reason sugar looks white. It's got a lot of little pieces. If you take a pane of glass and you bust it up into a lot of little fragments, it's a pile of white powder. Same with ice. When you bust it up into a lot of little pieces, like snowflakes, they look white. But they're really, really clear, just like glass is clear and salt and sugar are clear. So I have a thing where I have a color filter in my microscope. So the snowflake sits here, and I have a color filter, which for you photography buffs sits at a pupil, and so you don't really see the color filter. And so what I'm doing is I'm shining light through the crystal from behind. And if I just shine light from all angles, I get this first one over here. It's kind of bland. Okay, not a lot of life in that picture. Over there on the upper right, I take some white light from underneath, some red light from one side, and some blue light from the other side, and it gives sort of nice blue and red highlights. Sometimes I'll take light in there's some places where there's no light coming in. That gives more of a shadowed look. And it gives the crystal some sort of three-dimensional shading, so you can see more detail. Like look at the center of the snowflake. You can hardly see anything up here, but down there you can see a little more because of the structure, the three-dimensional aspects. And that's from the lighting. And then sometimes I use crazy rainbow filters just for fun. Okay, so I can I do try different techniques. You can light them from the back. You can light them from the front. When you light them from the front, they tend to look white, like snowflakes on your sleeve. If you look closely, they're not really white. Again, it's got clear places in it because the ice is clear, but all the edges look white. And so, okay. Sometimes I'll take a picture using instant light, so this looks a little more like what you'd see on your sleeve. Okay, but I like the colors. I go for the colors just because it's fun. That's my contribution to snowflake photography is adding color. It's pretty. You zoom in there and see some things. So this one, here's a nice example of a sort of a crazy rainbow snowflake. Some people think, I must be using polarized light or something, but no polarized light, just all this different colors coming in from the side. And they just come out looking like this. It's kind of neat. Sometimes I go a little too far, So, and it's fun. Okay. I don't know, just snowflakes, red, Christmassy, Here's one that sort of melted a little on the way down. Sometimes if the clouds are very high, they form and then there's nothing between the cloud and you, and so they're coming down, they just kind of evaporate on the way down a little bit, so it looks a little degraded, a little travel-worn, the snowflake. So let's take a tour. Let's go back to the beginning. You got your microscope, and let's look at everything. What do we see? What falls from the sky? So the smallest crystals, little tiny things, are little simple plates and columns, and these are around. And when it's very cold, you see these a lot because they're so tiny, they're very faceted. Sometimes you get a snowstorm that's made up of these things, and people call that diamond dust because you just see these little sparkles in the air on very cold days. You see that sometimes. And that's made of little tiny crystals, and they're very simple crystals. Okay? So those are the smallest, a fraction of a millimeter. Here's some more. Little prisms, a little plate, simple, not too many markings, nothing much to it. These are a fraction of a millimeter. Okay, you need a microscope to really see these well. This one's maybe a little more than a millimeter. As they get bigger, they get more structure. And the next step are these what are called broad-branched stellar plates. People like to look at snowflakes, you got to get them names. So we have names for these things. These are maybe 1 or 2, 3 millimeters, and you see they got some branching. Lots of surface markings. Here's a nice one. You can see the symmetry is kind of fun. I mean, look at, for instance, these lines. They just form a nice little hexagon all around the crystal, so they're very symmetrical. Sometimes I call this one the 6 pinheads. You can see these guys here. There's their arms and their legs, and there's their little pinheads. And so usually when you see little guys in the snowflakes, it's time to go inside and warm up for a while. So here's another one, just a nice little snowflake, not too complicated. Here's another one, very pretty. This was a cold day. This is probably minus 17, and everything looked like this. They were all, here's what you normally find. You just put a microscope slide out here. There was a lot of broken ones and a lot of sort of malformed ones, but they still had the same basic structure. Little tiny crystals, a couple of millimeters. Here's a much bigger one, probably 4 millimeters. This one has a lot of beautiful markings on it. Just another little crystal. So you see the guys are back. So I call this the Hallelujah crystal because they're Hallelujah. All right, so there's another one. I don't know. I take they're fun. You know, lots of things to see. One of the features of snowflakes are these ridges, and these, if you see these ridges very prominently, they're called sectored plates. The ridges, you can see in the upper right there, the ridges kind of divide the crystal into sectors. There's no real standard naming convention for snowflakes. I like to say it's like when you name bread or pasta. You know, it's just sort of infinite variety, and you can sort of draw the line somewhere. You got your wheat bread and your pumpernickel, or maybe, you know, a long skinny one's a baguette. Or, you know, it's just how you decide to name these things. And same with snowflakes. There's a spectrum, and we give them names. And people have been doing this for a long time. Here's another one, a lot of sectors. Duck feet, I call them, because they look like little duck feet. You see a lot of this. I mean, these sectored plate crews. Here's another duck feet. So some of these things you just see over and over again. So I just want to point them out. You know, lots of them. Here's, you can see the broad branch plates and the sectors. You know, just lots and lots of every, you know, they're all a little different. It's fun when you're photographing because you never quite know what you're going to get. I could say it's a little treasure hunt, and so you just see what you can find. Now here's one. You see a lot of this. It's called a rimed crystal. One of those little spots. I told you the crystal's forming up in the clouds, and the clouds are made of water droplets. Sometimes what happens is the crystal will form, and forms very nicely, but then it runs into a part of the cloud where the droplets are very dense. Okay, lots and lots of droplets, and just gets coated with these little droplets. And we call that rime. And so there's a snowflake that formed first in a nice region where there weren't a lot of droplets, and then it just ran into, it plowed into a bunch of droplets, and it got kind of covered. Sometimes this happens a lot, and there's a snowflake in there somewhere, and then it just ran into all these droplets, and they just piled on, and you get this very, it's called grapple, okay? Meteorological term. Now they get bigger, they get a little more complicated. You get stellar dendrites, stellar because they're star-shaped. Dendrite means tree-like. And so here you see main branches and side branches. They're still thin plates. If you look at them from the side, they're really very thin. And when they get a lot of branching, we call them fern-like stellar dendrites because they look like little ferns. Okay, and these are big. These can be 3, 4, 5 millimeters in size. So these are the ones are most prominent on your sleeve. Okay, here's a nice example, and here's another one. They're not all perfectly symmetrical. You know, a lot of people think every snowflake's perfectly symmetrical. No, that's not true. You know, when you photograph snowflakes, nobody wants to look at the ugly ones. They want to look at the nice ones. So you know, you get one of these, you throw it away. You just kind of say, well, you know, don't mind that. Here's a pretty one. So here's one. It's got some branching. It's got some plates, a little bit of rime on the inside, those little droplets. You know, this is sort of typical. They're all a little different. Here's a big, beautiful, this is like 5 millimeters across. This one I found in Sweden. It's a really beautiful example. These fern-like stellar dendrites are really common. You can find a lot of these. That's why people sort of associate these with snowflakes, because they're big and they're easy to see and they're common. This is a picture of my windshield one day after it, you know, there was just nothing but stellar dendrites covering it. If you like to ski and you want really soft, fluffy snow, this is the stuff, this fern-like stellar dendrites, because the barbs sort of don't pack very well, and so this is very, very light and not very dense. And so if you get 10 feet of this and you just jump in, you'll sink up to your waist. Okay, so skiers like this stuff. Okay, here's a really big one. This is 1 centimeter across. That's the biggest one that's ever been photographed, and the biggest one I've ever seen. Saw that one in Cochrane. It was very pretty. I mean, these big crystals falling around. These fell for 10 minutes, and then they were gone. And I got a few pictures of those. Now, columns. I showed you some of these before. I showed you those from the morphology diagram, too. These fall from the sky. You can see hollow columns, usually. You see the hollows. That's because the edges grow faster because the water diffuses to the edges more, and so they get these hollow regions inside. Okay. When they grow bigger, the hollows kind of split, and you get split ends, and they become needle clusters. And these can be big, 2 or 3 millimeters. You don't notice them so much. When they fall on your sleeve, it looks like little bits of hair, little tiny pieces of hair, so you don't notice it very much. But if you look at it, if you know it's there, you can find it. Some days, the whole snowfall is nothing but needles. So here again, I just put a microscope slide out, crystals fell on it, and that's what we had. Now here's something weird, capped columns. So what happens here is if the crystal starts out as a column, say growing around -5, -6, and then the conditions change. It moves, say, to a colder region, often because it's being blown up by an updraft, and so you get plates growing on either side of the column. So it's like an axle with 2 wheels. Here's one I photographed. Here's a picture. I just dumped it on the microscope slide. And I took the picture, and then I used my little brush, and I put it on end, and then I focused on the top plate and then on the bottom plate. And so you see it's 2 stellar snowflakes on the end of a column. Okay. Here's another nice one. So I have a question for you guys. How many have you seen capped columns? Sorry. How many of you seen one person? Oh, you guys. You got to get out there and watch. Okay, your assignment is to get a little magnifier. Even without a magnifier, you can see these with your naked eye. They're pretty common. Okay. Here's another neat one. It's just a column with very, very thin plates. Seen edge on. Okay. And here's this crazy one I showed you before. And so now, since now we understand how snowflakes work, we can explain this. Okay. What happened here? Well, first there was a needle. So it started growing around -5, -6, and it grew into a needle. Okay, slender column. And then it ran into some cloud, and it picked up a bunch of rime particles. And those little droplets froze on the needle and covered it with rime. But then it moved somewhere else where plates grow. And so plates started growing off those rime droplets, and the plates are all edge-on. And so you see, this is a single crystal of ice. The molecules are all lined up from one end. Why do I know that? Because the plates are all parallel. Okay, they're not coming out every which way. They're all lined up like sheets of paper. So that's a single crystal, and you can kind of tell the history just by looking at the shape. So there's a completely worthless skill if I ever knew one. So, all right. But after a while, you start to see some funny things. Like you might think, well, what about this one? Did you see it? This is a double plate. So think of a capped column, but the 2 caps are very close together. So here in the middle, that's the little column. This hexagon, see, there's a little out of focus. That's one of the plates, and then the other plate is behind. Okay? So if you look at it from the edge, it might look something like this. It's a different crystal, but it's you get the idea. And that's sort of a capped column, but their pieces are so close together, we call it a double plate. Okay? And here's another one. You can see something's out of focus there, so that looks like a normal snowflake, but there's the other one. And now I can go back to the first one. So you see it's 2 plates, one on top of the other, with an axle between the 2. Okay? Here's another funny thing. This is a split plate. So how did this happen, and what is it? Well, first of all, there's this little round thing. That's the column. It started out as a little column, then 2 plates formed on top of the column. But these plates are growing right next to one another, and they're competing for the water vapor. And so if one of them gets ahead, then it robs all the water vapor from its neighbor, and off it goes, and the neighbor is stunted. And so you see this half, these 3 branches are on one plate, and these 3 branches are on the other plate. There's the little diagram on the side there, so what you look like. And so it looks kind of like an ordinary snowflake, except it's messed up in the middle. Okay? It's got a little rime on it, too. Okay? Here's another example of that. So you see here's the column in the middle, and then 2 plates. There's one half, and there's the other half. And you can get these in all combinations. You get 3 and 3, or you can get 2 and 4, or 1 and 5. They're all out there. Okay? You don't really notice it until you sort of start looking closely. Triangular snowflakes. You can find triangular. Who knew there were triangular snowflakes? Okay? They're out there if you look for them. They're not, perfect triangles, but you see they're kind of funny looking. They're fairly common, if you look for them. I wrote a little paper on why these grow. It's not too bad. but they're obviously different. Here's another one. So 12 branched crystals. You can see 12 branched snowflakes too if you go out looking. It's really just like 2 6-branched snowflakes, one on top of the other. And these are fairly common as well. Here's another one. I think I put in, no, here's another one. Okay. And here's that collection board I showed you before. And you can sort of see, this is kind of a random shot, and there's a nice crystal, and there's a nice one. There's a lot of these grapple things. And over here, there's a 12-sided one, you see. So they're out there. That's what they look like. You can sort of spot them. You're pretty good at picking these things out. It's pretty good. Okay. And there's a whole menagerie of things. You can just start writing down what different kinds. And it's just crazy. There's all sorts of shapes. And some have, columns and plates all mixed together, funny patterns. So I wrote a book, A Field Guide to Snowflakes, and it sort of tells you about this kind of stuff. And it comes back to me for the physics. I look at all these crystals, and it's fun to look at them, but why are they there? Why do they have all these crazy shapes? Why so much diversity? Why all the different shapes? What's going on? And, what's the underlying physics? It all really comes back to this morphology diagram. This is sort of the key. This is the Rosetta Stone, if you will. And then these other crystals, these crazy things, they all just see different combinations of conditions under. And cloud's a crazy place. It can be warm on one side and cold on the other, and so lots of crazy things happen. But this is the basics. If you understand this, then you can kind of understand the rest of it. We don't understand this, so it's a problem. So I spent a lot of my time trying to figure this out. It's like, again, you start with all crystals, and you look at one, and there's these puzzles. What does the ice surface really look like? It's not a simple surface. Actually, there's something called surface melting, where the top layers will actually start to get disordered, and called a quasi-liquid layer. When these molecules are attaching to the surface, how quickly do they attach, and how does that work? And there's a lot of stuff going on at the molecular scale that I like to try to figure out, and how does that molecular scale physics translate into the shape of the snowflake? And why does it depend on temperature and give these transitions? And I'm still trying to figure out all that stuff. And I'm not going to tell you all the details. It's another lecture for another day. But I spent a lot of time doing experiments, a little more complicated than before. So I'm here's that tank I had before, and the crystals are growing. And now I put a separate little tank inside, a little chamber, and it draws some of those crystals in there. And I let them fall onto a substrate, a little glass disc, and they sit on there, and I position one crystal underneath the microscope. So I'm really trying to make this setup, where I've got a little chamber with some frost on the top. It's an ice reservoir, and a little test crystal. And then I make careful measurements of how that crystal grows. And I can change the temperature, because it's all controlled. I can change the temperature, and I can change the temperature difference, and so I can change how fast it grows. And, trying to use all this information to kind of figure out what's going on at the molecular level. And that and modeling, it's physics. We understand some of this stuff, just not all of it. So we keep going. Here's what it looks like in the lab. They're not just falling out of the sky anymore, so you got to make them. And so here's the big tank, about 1 meter high, and then the real experiment is down in this little thing, and there's lots of plumbing and cameras and a chiller and computer attached. So I'm doing this, I tend to make lots of little tiny snowflakes like this one. These are easier to do the physics on. They're little tiny things. They're maybe half the diameter of a human hair. And so I make these, and then we measure the growth rates and try to do all this. And so it's always fun when I'm doing a run. I tell my wife, I say, gotta go to work, dear. These snowflakes aren't going to grow themselves, Anyway, so I got a website if you want to go there. But I'm going to end, snowcrystals.com. I'm going to end with some movies. Because one of the things I do, in addition to just making little snowflakes and trying to understand the physics, sometimes I like to make big snowflakes. So I'll tell you a story, because we were doing this stuff. I was doing this stuff in this hardware. And I get a call from the BBC. And the BBC goes, we're making a documentary called Frozen Planet, and they wanted movies of growing snowflakes. And I said, nobody's ever made a good movie of a growing snowflake, because people made kind of lousy, low-resolution movies, but nothing very good. And they said, oh, no, this has got to go on HD TV, we want all new, nice movies. And I said, well, I think I know how to do it, because I've been working with this stuff, and I had some ideas. And so, for a small fee, we can try. And, they said yes. And so I got into the snowflake movie business, believe it or not. So let me show you here some movies. What do we got? Okay, let's see if I can get this to go. There we go. So we start with a little plate, a little tiny, well, I didn't stop it quite soon enough, but we start with a little prism that sits on a glass substrate. And then we sort of I make it grow. I actually just blow a little humid air at the thing, and it grows. It doesn't actually grow on the glass, it grows above the glass. So it's like a half of a capped column. There's a little column there, and then this thing sits above the glass. Okay. Now I have to put this on here, it's a real snowflake. I've shown this before, and people say, that was a great computer simulation you showed. No, it's not a computer. We don't even know how to do the computer simulations. We're trying. But we know how to grow them. It's easier to grow them than it is to make them on the computer. So there's that. Let's show you another one here. So let's see. We got another one? Yeah, another one. This one's good. All right, little tiny speck of a crystal. And now it grows. And you see these transitions, these little ribs. And then all of a sudden, now it starts to form branches. And then, it'll make plates again. What you don't see, these things don't happen spontaneously. What you don't see is I'm sitting over here at the controls going, let's make some. I want some plates. No, I want some branches. No plates, no branches. And so you can just sit there. It takes about 45 minutes. And so I watch this, and I'll sort of go, plates for a while. Yeah, plates. I want plates. And let's put a line on the plates now. And it's like, okay, enough plates. Now let's grow some branches. And I turn the knob, and okay, that's enough of the branches. Now let's make some plates on it, some little ribs on the plates. Now more branches. You get the idea. You just sort of like being a puppet master. So this time I started with 2 seed crystals sitting next to one another. And now you see they interfere with one another. These crystals are not pre-programmed to grow into nice symmetrical shapes. If they get interfered with, then the water vapor, they're competing for water vapor. And in the middle, there's just not enough water vapor for both of them, and so you get a region where there's just not a lot of growth. The growth is stunted. So they interact. And this, of course, happens in the atmosphere all the time as well. So they're not perfectly symmetrical, only if you get a nice isolated one. So here's one where I really went for the plates. Beautiful sectored plate there, and then some ribs, now some branches. I feel I'm getting kind of good at this. I can make them better than I can find them outside, or at least I'm getting there. So maybe the next generation. But it's very pretty, You get these nice snowflakes. So that's that. I think it's one of my favorites because it ends up so nice. So a little tiny speck again, and now the thing grows out. And I don't know. There's no exact formula for it yet. And I'm not controlling it by computer. I'm just sitting there with the knobs and kind of watching it. You got an hour to watch this grow, so it takes a while. But as you can see, you can get some pretty nice looking snowflakes this way. So I'm kind of trying to perfect this, and we'll get really majestic looking snowflakes, but maybe later. So, all right, and we'll stop with that. So, thank you.
Okay, ladies and gentlemen, we will open the floor to questions. And why don't we start right here?
I was just wondering, is there a difference in the way that frost forms as opposed to snowflakes?
Okay, frost, yeah. When frost forms, it's basically the same idea. You've got water vapor in the air, and it condenses onto something. If there's an ice particle in the atmosphere, these things, these little droplets freeze, and that's what it condenses onto. But on the ground, you've got grass, and the water vapor will condense on the grass. And if you get out your magnifier and look at the grass, you'll see the same kinds of crystals on the grass, so frost crystals also. So it's the same basic process, yeah.
Let's go right here to my right.
What do the crystals look like that come out of snow guns on ski hills?
I didn't put that slide in. I should have, but it's a very different process. What happens is with a snow gun is you start with a nozzle that shoots out little water droplets. So it's an atomizer, shoots out little water droplets, and that's mixed in with compressed air. And the compressed air expands and it gets cold, and so that freezes the droplets, and it sort of freezes them as they're expanding. And then there's a big fan that blows it out into the slopes. And so so it's a different process. You got these droplets, and it gets really cold. It's so cold they just all freeze. And to make a snowflake takes half an hour. These things, they're very much faster. So you basically just freeze the droplets and then blow them off. So if you take a picture of this, and I've done this, what you see is just a bunch of little blobs of ice, little round frozen droplets, about what you'd expect if you, froze this stuff in your freezer. So it's a very different process.
Let's go to the Twitter feed. Question from Ed Dote. What do we know about the effect of the presence of different gases in the atmosphere on crystal formation?
That's good. There's that's a whole side of the subject I like to think about is what happens. And we work on this in the lab. I'd like to put in different chemical impurities into the air and see how that changes the crystal growth, because it's really a chemical catalysis problem. The catalysts will change how chemical reactions form, or what the rates of chemical reactions. And similarly, chemicals can change the rate of crystal growth. And strange things happen, like you don't get any thin plates if you have a lot of impurities in the atmosphere. So if the atmosphere is polluted enough, you would not get beautiful snow crystals, because those are the first to go. But of course, chemistry is a big business. There's a lot of things going on, and that's at pretty high concentrations. And so if you look at the winter air, it's pretty clean, and so there's not a lot of effect of what's up there, because there isn't that much up there.
Let's go to the question on my left.
Did you ever grow a column snowflake?
Do I grow columns? Oh yeah, all the time. I like to grow columns too. They're not so much fun to show audiences. So.
And I believe another question here on the right.
Why does the snowflake grow if you blow on it?
Well, this thing's sitting on a piece of glass, and there's not much going on because it's right next to glass, and so you got to get some humid air into the snowflake. You got to get some water vapor. So what I do is I take some slightly humid air, and I just have a little funnel, and I blow the humid air onto the snowflake, and that's where the high humidity makes the thing grow. So.
And a question to the left, my left.
Yes, I noticed something really unusual with the snowstorm of '78 we had, where it really wasn't snowing down, it was snowing horizontally. It was coming off the lake, blowing off the lake. But what I really found strange is one day I was out in the field and I seen real fine snow on a really cold day lifting off the field and rising up. Have you ever seen that?
No, I haven't seen that, but I've learned in meteorology, you never say never, because there's a lot of crazy stuff that happens. And, there are a lot of these events, like snow rising up from lakes. It might be very rare, but the conditions can be just right to see some crazy stuff sometimes. So I've never seen that, but that doesn't mean, there's a lot of weird stuff out there.
Let's go back to the Twitter feed for one. And Professor, this is what we were talking about on the way over. So it's awesome science and photos, but what are the practical applications of studying crystal formations of snowflakes?
Well, I got started from looking at crystal growth in general. And, eventually I'll get back to that. But, at some point in the process, you can't think about the applications. You just have to focus on solving this one problem. But one of my answers to this question is that I've written a bunch of books on snowflakes, and those snowflakes put my kids through college, so that's can't get any more applied than that.
Let's take two more questions. One here, and then we'll follow up on the left.
Does dust particles in the air have any effect on the production of snowflakes?
Absolutely. When when you're forming ice, it's always a nucleation problem. That the ice has to nucleate on something. And if you have very, very pure water droplets, for example, in a cloud, those pure water droplets are no dust. If there was pure water droplets, they would not freeze until the temperature got down to about -40. Okay, but in real clouds, the droplets start freezing at much higher temperatures, around -10. And the reason is that inside of each droplet is a little piece of dust, because when the cloud was forming in the first place, you just had humid air, and you cool the humid air down, the water precipitates out. Basically, like dew comes down. Dew will deposit on the grass, but in the clouds, the dew deposits on something, it deposits on the dust. And so every little droplet's got a piece of dust in it. And that dust affects how quickly it turns to ice. So.
Okay, when I said 2, I meant 2 more now. 1 here, and then we'll finish in the front.
I sort of vaguely remember reading or hearing somewhere that if you look at really complex snowflake structures, like some of your fern-like ones, that they have a bit of a fractal structure to them. Is that true?
Yeah, it can be a fractal structure. Fractal mostly means self-similar, and if you grow the crystals big enough, you'll find the branches have side branches that look like the main branches, and the side branches have their own side branches. That's only when they get really big. And so most of the time, these crystals, there's not a lot of fractal behavior, so it's not a sort of a good paradigm to sort of use to think about the problem. But it's there.
And our last question right here in the front.
Have you noticed any difference in the formation of snowflakes with the global warming that we're moving into?
Well, if you go back in history, a lot of some of the best the early snowflake photographs were taken in Vermont, and there's a lot of snowflakes into the lower 48, but it's gotten warmer. And so you got to go further north to get the nice snowflakes now. So yeah, if the climate is getting warmer, then it will be harder to find these nice snowflakes. So I got to go out there and photograph them now before they disappear. But yeah, it's really a temperature thing. I mean, these big, beautiful stellar crystals form around -15. And that's the only temperature they form at. So if the winters get warmer, then there'll be fewer big, beautiful stellar crystals in the lower latitudes. So,
ladies and gentlemen, please join me in thanking Professor Kenneth Libbrecht.
Thank you.
This was the probe that was originally attached to the Cassini spacecraft at Saturn. It was bolted to the side, the Huygens probe. It landed in 2005. Shown on the right-hand side there, they have it sort of situated there looking a bit like a mushroom. Get an idea of the scale. You'll notice on the far left-hand side there's one of the technicians standing there. So what you're actually seeing on top is the heat shield that came away, but the actual craft is hanging upside down underneath. So when it actually parachuted down to the surface, it was in the reverse orientation to what you see it sitting there in the lab. So
So where's the technician?
if you look at him by the railing on the left-hand side, you actually see half of him hanging there. So the actual craft itself, the white bit that's upside down, is 1.3 metres across, weighed 318 kilos, and it was designed so its battery would last. They thought it would go for about 30 minutes after it landed, but it ended up going for 90 minutes transmitting back. They were actually very lucky because, of course, it sat dormant for 7 years before it was actually activated. And when they came to activate it, they found it had major software issues in the firmware, so they couldn't actually alter it. And they really only got half of the transmissions that they were hoping for on the way down for that very reason, unfortunately. So as Cassini let go of it, it started communicating back to Cassini, and then that larger craft up in orbit was then going to broadcast back to Earth. So it took it about 2.5 hours to descend through the atmosphere of Titan, which is Saturn's largest moon. So very, very dense, mainly nitrogen and methane with traces of hydrogen and I think ethane and other hydrocarbons in there as well, but mainly nitrogen and methane. When you actually see the images, the actual images as it descends, look at the bottom right and it'll actually show you the speed and the altitude as it's coming down through that 2.5 hours before it clears the haze. Now when it hit the surface turned out to be a bit slippery. It's temperature 94 Kelvin, which is minus 179 degrees Celsius, so very, very cold. At that temperature, water is tougher than steel, obviously very brittle. And some hydrocarbons are a liquid at that temperature, so that you can have water on the surface, or the equivalent liquid on the surface, so you can have lakes of hydrocarbon and rivers, and indeed they found evidence elsewhere on Titan that, that these lakes and that can occur towards the poles. As it actually came down, underneath the craft as it came down, it had what they call a penetrometer. So it was designed to see how far it could punch its way into the surface to figure it out. So it measured the force of the impact effectively as a function of time to try and see if they could actually work out what it was. As it turned out, it actually landed on one of the water pebbles that was sitting on the surface. So they look like large boulders, but that's just a foreshortening effect. So what you'll actually see are pebbles of water about 15 centimetres across, so roughly 6 inches across. So we hit one of those, bounced off and slid across the surface a bit for about 40 centimetres, even though it's 318 kilos of the stuff when it came down. There was actually images of dew dropping out of the sky that they managed to capture in the 90 minutes while it was there as well as the heat haze from a lamp that they had to shine onto the surface to try and analyse what was actually on the surface, and you could see the rippling effect just from turning on the light, because you're talking really, really low cryogenic temperatures there. And with that, we will close the meeting relatively early compared to some we've had, and we'll see you hopefully at the April meeting. Thank you.